Okay, I'm going to go through a quadrilateral kind of property review. This is just kind of nothing new, just kind of reviewing some of the properties for each of the individual shapes that you might use in solving your problems. So if you have just a general quadrilateral, just like I said, a general four-sided polygon, probably the property you're going to use the most is that we still do know that all the angles add up to 360. Okay, so we have that angle, that angle. None of the angles have to be congruent, but we know for sure that if you have a four-sided quadrilateral, that they have to add up to 360. So that's certainly probably the only property that's general to a quadrilateral. If we move to a parallelogram, we start adding a ton of more properties. So for a parallelogram, we know that side is congruent to that side. That side is congruent to that side. We also know that this is parallel to this, so they have the same slope. And when I said these two are congruent in terms of their lengths, that means they're the same size. You know, they're both 5 feet or 3 inches. You'd use the Pythagorean theorem to prove lengths, and you find slopes to prove parallel, and that guy is parallel to this guy. Okay, what else do we know? We know the diagonals bisect each other. So if you had that diagonal and that diagonal, now the diagonals are not the same length, but they do bisect each other. So somehow if you knew that was 5, you know that was 5. If you knew that was 7, you would know that was 7. Okay. You also know that angles are supplements. So this angle is in fact congruent to this angle, and this angle is congruent to that angle. And you know that these are supplements, these are supplements, these are supplements, and these are supplements, meaning this plus this is equal to 180. Again, these are parallel lines. These are really just alternate interiors. Okay, so there's all sorts of things you know about a parallelogram, and then you can use it to solve for a variable. You know, if I labeled this 2x plus 5 and this 3x plus 2, you could set them equal to each other because you know they're the same length. If this was an angle like 3x and this was an angle of 5x plus 10, you could set them equal because the angles are congruent, meaning they're the same measure. Okay, if you go to a rectangle, we have some additional properties. So we know this and this, and this and this, and we know they're parallel, and yada yada yada. A rectangle is a parallelogram. It's just a special parallelogram. So for a rectangle, we know that all the angles are 90 degrees. We can prove something's a rectangle by proving that it's got 4 right angles, and then it has to be then a parallelogram. We prove things are right angles because of opposite reciprocal slopes. So this is a vertical slope and this is a horizontal slope, but if it was tilted, we'd want to show opposite reciprocal stuff. We also lots of times look at diagonals. Now in this case, the diagonals bisect each other and the diagonals are congruent. You can just see they are the same. They aren't perpendicular, as you can see. It's clearly not 90 degrees, but the diagonals now are congruent, and you can use the Pythagorean theorem to find the length of diagonal if you know the two sides. Maybe you know the area. The area here is base times height. The area here is also base times height. A square just adds one layer. Certainly they're all 90 degrees, and then all the sides are the same. We add the fact that here the area is base times height, or length times width. Here's base times height. Certainly, since the base and the height are the same, a lot of people just say side squared, but it's also 1/2 of the diagonal square. Now here, we add another property of the diagonals. The diagonals they do bisect each other, they are congruent, and we form a 90-degree angle there. So they can do stuff, like ask you for this and this, if you know that. It also adds in the special right triangle, and then if you know you have a square that is 4 here, that's 4, then you know the diagonal is 4 radical 2, because we know how a 45, 45, 90 triangle works. So they like to do stuff with squares in that. If we move to a trapezoid, trapezoid really is just at least one sides are parallel. So let's say those are the parallel ones. There's really no relationship between these angles and these angles. But we do know that angle 1 and angle 2 are supplements, and angle 3 and angle 4 are supplements. And we know that angle 1, 2, and 3, and 4 add up together to give 360, as in all of these do. But there's no relationship between 1 and 3. And that's honestly about it for a trapezoid. To prove something's a trapezoid, you just prove it's got one set of parallel sides, and that's just to say they have the same slope. The area here is 1/2 the height times b1 plus b2. Okay. Now an isosceles trapezoid, that goes one step further. This is clearly parallel to that, but this is congruent to that. And because of that, it's kind of like just an isosceles triangle. If you extend this and make it into a triangle, we know that the base angle theorem is true. Okay, so those angles are congruent, which means those angles are congruent because you could have just flipped the trapezoid up the other way. And so now we have two pairs of congruent angles. Consecutive angles are actually congruent across this and across that. The area is still the same because it's still a trapezoid. I guess I'll say one more thing. Obviously, both for an isosceles trapezoid and a trapezoid, we can have this mid-segment. The mid-segment theorem. The mid-segment just says that the mid-segment's length is equal to the average of the two bases. Okay, so like capital M equals 1/2 b1 plus b2. Okay, let's go to a rhombus. So a rhombus is a parallelogram, but it's a special parallelogram in that it has this. Okay, now you can ask yourself other questions. Since it's a parallelogram, well, we know this and this, and this and this are equal because it's a parallelogram. Are the diagonals congruent? Well, just look at them. Look at that diagonal versus that diagonal. They're not congruent. This one's way longer. However, they do still bisect each other because it's a parallelogram, and in this case, they are perpendicular to each other. And so that's one more feature that you can use on a rhombus. And again, once you have something perpendicular, then you can start doing the Pythagorean theorem that if you know somehow that this is 3 and this is 4, then all of a sudden you know that that guy's 5 because of the Pythagorean theorem. Okay, so anytime you can get some perpendicular stuff, whether it be in a square or the diagonals of a rhombus or the corners of a rectangle, you're going to start using the Pythagorean theorem to find certain values. What else for a rhombus? These angles are bisected. Same thing in a square, it forms 40, 45, 45. These angles are not bisected. Okay, that's probably it for a rhombus. We can say base times height is the area, or we can do 1/2 d1 times d2. Okay, and then we get to a kite, and again, this is the definition of our kite. We have that to be true. We have this angle is congruent to that angle. Those angles are not congruent, but those are. And then, just look, are the diagonals congruent? No, this one's clearly longer. Are the diagonals bisected? Well, the short one is bisected because that guy equals that guy, but the long one is not bisected, but they are perpendicular to each other. And again, you got to go through of all these properties. Like these diagonals are congruent, but they're not perpendicular. They do bisect each other. These bisect each other, not perpendicular, not congruent. Squares, like everything, right? Diagonals are congruent, diagonals bisect each other, diagonals are perpendicular. Rhombus, diagonals bisect each other, diagonals are perpendicular, diagonals are not equal. Go to the kite. One of the diagonals gets bisected. The diagonals are perpendicular. The diagonals are not equal. The area of the kite is just like the version of the rhombus, because a rhombus is by definition a kite, right? A rhombus is a kite and a parallelogram, just like a square is kind of everything. Okay, so we have kites. And again, once you have a kite, then you have that same thing that if you know this is 4, you know this is 4, and you know this is this is 7, then you can use the 7 and the 4 to find the this side length, because the Pythagorean theorem would say 4 squared plus 7 squared and things like that. Again, you're going to do a whole review of the properties and solving for x and solving for y and using mid-segments and finding area, using the Pythagorean theorem, using slope, setting two things that you know have to be congruent and setting them equal to each other, taking two things that you know are this plus this equals 180 and solving. So you're going to do a lot of problem solving, but it really comes down mostly to just kind of understanding those properties. If you just draw out the general shape and you look at it, you probably can just tell what the property is. I mean, I think it's pretty obvious that for a kite, the diagonals are perpendicular, that one is bisected, but this one isn't bisected, and the diagonals aren't the same length. So you can kind of get an idea of what's going on here. Look at a parallelogram, right? These are not the same length. They're not necessarily perpendicular. They're only perpendicular if it's a rhombus or a square. Okay? So hopefully you have a good start on reviewing the properties of these things, and again, using them to solve for problems.